Okay, let's get into our first chapter of applied solar energy systems. The first one we're going to look at is active solar thermal energy. So, quick intro here. Solar energy applications are generally classed into three categories. So we covered it earlier in the beginning of solar energy fundamentals, but I'll recap here. An active system is basically concerned with harvesting thermal energy through the use of solar collectors that employ active mechanical components, such as pumps, to collect and transport heat. Passive solar energy systems typically are associated with a built environment, so an environment that collects and transports heat by non-mechanical means. Then the last one is photovoltaic, which utilizes solar energy to directly produce electricity. In this chapter, we're going to be dealing with active solar systems. So let's look at a solar collector. See in this diagram here in the upper left-hand side of the slide, it is a typical flat plate collector. Flat plate collectors are mainly and widely used in residences and in commercial and industrial buildings for hot water and space heating. This example is what would be called is mounted at a fixed angle on a roof, that is south-facing, right? Since the angle of the sun would vary to the south in the winter and over top in the summer, so a south-facing roof would be the best choice. On the bottom right-hand side, you have what's called a parabolic trough collector. The parabolic trough collector possesses the ability to track the altitude angle of the sun. The parabolic trough here focuses the sun's rays on a single pipe, as you can see right here, and provides higher water temperatures than what a typical flat plate collector can do. And then there's also this another active system called a heliostat. The heliostat basically has a central receiver, which is here, that receives concentrated sunlight, which is reflected by this array of mirrors. And it reflects all the sun to this concentrated point for the purpose of boiling water in order for that water to serve as part of a modified Rankine cycle to produce electricity. These solar collectors, so any of the solar collectors, can be either tracking or non-tracking, right? Tracking collectors, as their name implies, track the motion of the sun about a single or dual axis, right? So you can have here an axis of rotation as well as control the tilt angle to make sure that that follows the sun's path in order to collect the sun's energy as best as possible. You also have tracking trough collectors too, which basically do the same thing with an axis of rotation in this direction, as well as an axis of rotation about the axis of the water pipe. The focus of this chapter, though, that we're in, is on flat plate collectors, since they are probably the most frequently used. Generally, flat plate collectors, solar collectors, are used to heat water for domestic and or for space heating purposes. So here in this simple diagram, you have a collector, collects the energy of the sun, exchanges with a storage tank, and then a storage tank basically goes onto some sort of heating load for a building where there's some auxiliary system to add to it to make up for what this collector can't do. Here's what the innards, I guess you could say, of a solar collector could look like. The collector components are contained in an enclosure that provides structural support. Glazing, which is basically a window, right? Glazings are transparent cover sheets, typically made of glass with a high solar transmissivity that provide protection and pass most of the solar radiation. Flat plate collectors without glazings are called unglazed. The absorber plate is made of a material that has a high solar absorptivity and a low emissivity. Water flowing through the tubes here is heated by energy from the absorber plate. And to minimize heat loss, the collector bottom, which is in contact with the absorber plate, is insulated. So looking at this diagram, right, we have the sun. The sun emits a certain amount of irradiation. That irradiation comes incident onto the solar collector. Some of it's absorbed, and then some of it is lost, right? So again, you have solar collector absorbs a certain amount of energy. It's going to lose a certain amount of energy to the environment because the solar collector is going to heat up to a temperature that's greater than ambient, so it's going to lose some energy to the environment. And the difference between what's absorbed and what's lost equates to what we would call useful thermal energy, and that thermal energy goes to increase the temperature of the water. So again, you get this MCPT, this enthalpy in, right? If you remember, enthalpy in thermo can be approximated as CPT. So if you take the mass flow rate times the CP of the water multiplied by the temperature difference, you get the heat being used to heat up the air. If you do or not to heat up the air, to heat up the water. If you're going to do a quick heat balance, you would get that, again, as I mentioned in the prior slide, the useful amount of energy that you get is going to equal the absorbed energy to the collector minus the amount that's lost. The absorbed energy can be quantified as a function of the irradiation intensity, the area of the surface area of the collector multiplied by the transmissivity and the absorptivity. So again, each of these parameters are the following. The lost solar, the lost energy in the form of heat can be quantified as a function of the convective loss in the environment. So you end up with the area of the collector multiplied by the conductance multiplied by the temperature difference between the average temperature of the collector minus ambient air. So again, each of the parameters are the following. So if we were to go ahead and take this, the absorbed amount of heat and the lost amount of heat, and plug it back into this equation, we would end up with the following. And then that would equal the mass flow rate times CCP times the temperature difference between the water exiting and the water entering the collector. Again, which is the useful energy, right? The useful heat is results in increasing the temperature of the water entering the solar collector. Consequently, the efficiency of the collector will be quantified as the amount of useful heat transfer that's received divided by the incident irradiation from the sun. So if we were to actually go ahead and plug in this the Q useful into this efficiency equation, we would end up with the following. And this efficiency equation, again, which is just after the algebra has been done, this final version of the efficiency equation is actually used often in order to quantify performance of different solar collectors. Basically, the properties of different typical flat plate collectors, categorize them according to their properties. Again, the transmissivity times the absorptivity is part of the efficiency equation, as well as the conductance between the plate and the ambient air. You can see here this graph. On the y-axis, you have efficiency. And on the x-axis, you have a parameter which basically takes the average air temperature, the average temperature of the collector minus the average air temperature divided by the solar irradiation. You can kind of see the decrease in efficiency over the increase of the x-axis value based on the based on the type of cover it has. So these type of performance criterion are typical for flat plate collectors. So that simple analysis basically expresses the collector efficiency in terms of average collector temperature. So you can actually go ahead and take that equation and modify it to include the temperature of the water entering into the collector. It also includes, I'm not going to go through the algebra with this, but this equation also includes what's called a solar collector heat removal factor. I've always kind of called it a fudge term, but this equation is an important equation, and it's named the Hottel-Whillier-Bliss equation. It's considered to be the most important expression associated with flat plate collectors. And it basically classifies collectors according to, in terms of this equation, which is basically a line, right? So if you consider the efficiency to be y, we consider this part of the equation to be the y-intercept. This portion can be considered the slope, and this portion can be considered x. So you can actually quantify this in terms of a linear line, y equals mx plus b. We would be able to go ahead and look at the efficiency of the solar collector as a function of all these parameters, basically as the inlet, mainly as a function of the inlet temperature of the water going into the collector. Collector data are usually represented in terms of the intercept in that equation, which is the heat removal factor times transmissivity and absorptivity, and the slope, which is the conductance between the collector and the air multiplied by the heat removal factor. So I'll go ahead and stop this video here, and we'll start the next one with an example problem.